Welcome to this video on finding the total voltage at a point in a field. And here, of course, we're talking about the concept of superposition. Now remember that this is just the more official way of describing the overlap of the electric field, which we had talked about before, at a particular point due to more than one point charge. So for instance, if I took a number line like this, and on the number line I placed two charges. Let's say I placed a positive charge here and I placed a positive charge here, and let's say that the distance between them is d, and I want to figure out what is the electric field at this point that's exactly in the middle of d. We'll call that position d over 2. And what we had to do in this circumstance, because these were point charges, we could use this electric field equation, that is the electric field at some position r away from a source charge q or a point charge q. Obviously, if these were not point charges and maybe these were lines of charge or something else, then you would have to adapt this equation. But either way, the first step in this process was to look at what the direction of the electric field is at this point due to each of these charges individually. So this positive charge, obviously we draw field lines pointing outwards. So at this position d over 2, the electric field would be pointing to the right. And this positive charge over here, all the electric field lines would point away. And so at the position d over 2, the electric field would be pointing to the left. So if we use the traditional positive x direction to the right, negative x direction to the left, what we could say is the electric field due to, let's call this one E1, was positive E1, and the electric field due to charge 2 was negative E2. Now we could show here that the net electric field was equal to K times Q over R squared, okay, and this one will make this the positive one from E1, okay, and then we have E2, but it's negative because it's pointing in the opposite direction. And so you can see here very clearly, because they both have the same distance away, which I could have written in as d over 2 over here, this all just sums to 0, and I have 0 newtons per coulomb of net electric field. Now if you recall, it became a lot more complicated when I had some configuration where there were two dimensions at play and I wasn't just figuring out the net electric field within one dimension. So there was the example where we had placed the charges at the corners of a equilateral triangle, and we were trying to show how the electric field was 0 at the centroid, and that made us have to calculate the components of the vectors, add all the components and then put them all back together, and it was very complicated. And the whole reason that this is a little bit more cumbersome is because electric field is, of course, a vector quantity. And vector quantities require that we resolve the orientation of the vector at every specific location. The nice thing about voltage, also known as electric potential, is that it's not a vector quantity. Voltage or electric potential is a scalar quantity, meaning that we do not have to resolve the direction and just the magnitude of the charges at a specific location. So let's go ahead and take a look at the same scenario over here, but now we would like to know what is the electric potential at this point due to each of the point charges. And so what we're going to do is I'm going to write down some information here. So I'll say Q1, and I labeled these E instead of Q. I apologize for that. So we have Q1. Now Q1 is contributing a potential V1, okay? And we're going to write down the electric potential equation for a point charge. So KQ1 over R instead of R squared, of course. And then to get V2, because of Q2, we're going to write K times Q2 over R. Okay, so you see they're very similar to these two equations. Now I was sloppy over here on this equation and I didn't write the absolute value into this equation. Now remember, because the electric field is a vector, we have to make sure that we don't infiltrate the direction E with the charge sign, because then that would manipulate or influence the direction E. And those two things are not the same kind of negative sign or positive sign, if that makes any sense. Now over here for the electric potential, the two Q1 and Q2, in these equations, we are not dealing with an absolute value because this is not a vector. V2 and V1 are not vector quantities, they're only scalar quantities. So we don't really care about the direction or the orientation of V because there isn't one. Okay? If you recall, voltage or electric potential is measured in joules per coulomb, which is the same thing as a volt. And a joule per coulomb is an energy derivative measurement. And so when we're talking about the certain amount of energy that's being contributed, energy doesn't have orientation, if that makes sense, right? We can be putting energy into a system or taking it out, but the direction at which energy comes into the system is irrelevant because it's just all added together as the total energy that's coming into the system. Okay, as long as it's coming into the system, we don't care from which direction or in which orientation. That doesn't even really have any meaning in this case. So what we're going to look at now is how would you figure out the potential at this point d over 2 because of the fact that this is a scalar and these are not absolute values anymore. Well, it's actually a lot easier because what we have to consider now, and I'll be a little bit clearer on this time, instead of writing r here for this specific example, I'm going to change r to d over 2, right, because that's the actual distance that I'm dealing with. And all I have to do is just add up v1 and v2. It doesn't matter the direction because direction doesn't have any meaning here. So I'd factor out k, and all I need to do is do q1 times 2 over d, okay, because this is a complex fraction, right, plus q2 times 2 over d, and whatever that ends up being, that's the answer. And so it's actually a lot easier to do this situation than it would be if we were dealing with the electric field. So it's very straightforward and it makes it so much easier. If you think about this example with the charges on the corners of this electric configuration that was an equilateral triangle, now we don't really care about the directions. We literally add up whatever distance this is, let's call that R1, this distance, which is also R1, and this distance, which is R1. I literally just have to calculate V for each of those distances. Obviously there we'd be using R for this statement, and I would actually just be calculating the addition of all three. It doesn't matter what direction they're pointing. So the electric potential is a lot easier to figure out, and it's just the addition of all of them. So even where the electric field cancels out, that might be the point where the electric potential is at its highest value, which is something that is important to think about as it's compared to the electric field. Now, if we have a negative charge, we do have to include the negative as part of this, and then you see we'll actually be subtracting the values from one another instead of adding them, because this is not an absolute value. So the kind of charge here is important. So I will leave you with that, and if you are interested in doing some practice problems to make sure you understand it, there were some linked below.